For pretty much our whole lives, the technology we use has just kept getting faster, smaller, and more powerful, almost like it's magic. But that magic, well, it's running right up against the fundamental laws of physics. We are now entering a totally new era for the chips that run our world, an era so incredibly small, we have to measure it in atoms. So let's decode what that really means. And look, this isn't just some abstract, theoretical question. This is the very thing that keeps engineers at the world's biggest tech companies up at night. Think about it. Our entire digital life, everything from the phone in your pocket to the artificial intelligence that's shaping our future, it's all built on one simple promise: making chips smaller and more powerful year after year. But what happens when we can't shrink them anymore? What happens when we finally hit that wall? For over half a century, technology has basically marched to the beat of a single drum, Moore's Law. The idea was pretty simple. The power of our microchips would roughly double every couple of years. And that relentless pace is exactly why we went from computers that took up an entire room to the literal supercomputers that we all carry around in our pockets today. It hasn't just been progress, it's been the engine driving our entire modern world. But the scale we're talking about now has completely changed the game. For decades, we measured these things in nanometers, that's billionths of a meter. Now we are officially entering what's called the Angstrom era. Okay, so what's an angstrom? It's about the size of a single hydrogen atom. At this point, we're not just manipulating materials anymore, we're building things with the atoms themselves. And down at that level, believe me, the old rules just don't apply. Okay, so to really get a handle on the insane challenge of this angstrom era, we've got to take a quick look at how these incredible little devices are even made. And honestly, the best way to think about it is like you're building a city. Except the city is billions of times smaller than the tip of your finger. So this whole construction phase has a name. It's called front-end fabrication. And it all starts with the land, which is this perfectly pure, polished disk of silicon called a wafer. And on top of this tiny piece of land, engineers build an entire metropolis, complete with billions of skyscrapers, highways, and power grids that eventually become the chip circuits. And building this city is this incredibly delicate, repeating dance of adding materials and then taking them away. They use beams of light to project a blueprint onto the wafer. Then they etch away materials to carve out structures. They add new layers of metals and insulators. And then they polish everything perfectly flat before starting all over again on the next floor of the city. This cycle repeats hundreds of times, all happening in clean rooms, thousands of times more sterile than a hospital operating room. It's just wild. So, in this vast digital city, what are the most important buildings? Well, they're called transistors. And these tiny, tiny structures are the real heroes of our story. At its heart, a transistor is really just a simple electrical switch. You've got a source where electrons come in, a drain where they go out, and then a gate, which is the actual switch. You apply a little voltage to that gate and boom, the switch is on. That represents a digital 1. You take the voltage away, the switch is off, a digital 0. A modern chip is made up of billions and billions of these switches, all flipping on and off. Now, for decades, these transistor switches were flat, or what they call planar. But as engineers kept shrinking them, they started to leak electricity, kind of like a dripping faucet. This wasted a ton of power and generated a massive amount of heat. The solution they came up with was just brilliant. Instead of a flat switch, they turned it on its side. They created what's called the FinFET, where the channel is a raised 3D fin, which lets the gate wrap around it on 3 sides. This gave them way more precise control and basically slammed the door shut on all those wasteful leaks. The FinFET was the hero. It single-handedly saved Moore's Law for over a decade. This incredible feat of engineering is exactly what powered the jump to the 5nm and 3nm chips that are inside the very devices that we all use every single day. But every hero has its limits. The incredible shrinking act kept going. And now, the fundamental laws of physics are starting to fight back, hard, against the FinFET design. The new battleground is the 2nm frontier. As we get closer and closer to this impossibly small scale, the FinFET, our hero transistor, is finally reaching its breaking point. So here's the problem. At 5 and 3 nanometers, the FinFET's 3-sided gate worked great. It could control the electron leakage just fine. But when you try to shrink it down to 2 nanometers and smaller, the channel just becomes too short. And those little leaks, they become a flood. The chips overheat, they waste power, and you actually stop getting any real performance boost. You hit a wall. As one of our sources put it so perfectly, physics has once again caught up with human ingenuity. That FinFET architecture, which was such a revolutionary solution just a few years ago, has now reached its fundamental limit. So all of this brings us to a really critical moment. The whole industry is facing a crisis that doesn't just need a small improvement, it needs an entirely new way of thinking, a whole new paradigm. All right, so let's recap where we are. The FinFET design that served us so well for so long has officially hit a physical wall. Trying to shrink it anymore just creates more problems than it solves. Too much heat, too much wasted power. And for the first time in decades, the steady, predictable march of Moore's Law is in real jeopardy. To keep our digital world moving forward, we don't just need an upgrade, we need a revolution.
You know that device you're watching this on? It's about to get a massive upgrade. Seriously, we are talking about a leap in technology that we really haven't seen in over a decade. And it's all thanks to something called the N2 process node from TSMC. Now, this isn't just some small incremental improvement. This is a fundamental, ground-up change in how we build the brains of all our electronics. The FinFET transistor. For more than 10 years, this tiny little workhorse has been the absolute bedrock of everything, from our phones to our data centers to our cars. But after all that time, it's finally reaching its limits. It's just run out of road.
So what exactly is a FinFET? Well, it's a pretty clever piece of 3D engineering. Just picture a tiny vertical fin sticking up, made of silicon. The gate, which acts like an on-off switch for electricity, wraps around this fin on 3 of its sides. That's how it controls the flow. And this is where we meet the villain of our story, leakage. You see, as we kept shrinking those fins smaller and smaller to cram more of them onto a chip, they started to get leaky. Electrons began to slip right through, even when the switch was supposed to be completely off. And all that leakage, it's just wasted power and a ton of unwanted heat.
So to stop that leak, we needed a totally new approach, a whole new design. Enter the Nanosheet transistor. This is the absolute star of the show for the N2 node, and it completely rethinks that fundamental switch that powers our entire digital world.
The idea behind it is kind of brilliant. Imagine you take one of those vertical FinFET fins, you rotate it 90 degrees so it's laying flat, and then you slice it horizontally into several incredibly thin stacked ribbons of silicon. Now, this is why it's called gate-all-around, or GAA. The gate material literally flows into the gaps between these ribbons, completely surrounding each and every one. So instead of having a grip on just 3 sides, we now have a full 360-degree clamp on the channel where all the electrons flow. So let's just boil it right down. A FinFET, it had a good 3-sided grip, but a Nanosheet, it has an absolute 4-sided grip. This gives it just incredible control over the flow of electricity, and it basically slams the door shut on all those pesky electron leaks.
But wait, there's more. This new design unlocks some amazing flexibility for chip designers. For the first time, they can actually change the width of these sheets. So if you need raw, unadulterated power for gaming, you use wide sheets. Need to just sit power for your smartwatch? You use narrow sheets. It's a total game changer.
Okay, so all this clever physics is really cool, but what does it actually mean for us in the real world? Well, this isn't just a science project. It leads to some truly staggering improvements in performance and, maybe even more importantly, power efficiency.
Let's talk speed. Compared to the very best chips out there today, N2 gives you a solid 10 to 15% speed boost for the exact same amount of power. That means your phone feels snappier, apps open faster, but your battery life doesn't take a hit.
Now, flip that around. What if you care more about battery life? Well, at the same speed as today's chips, N2 slashes power consumption by a massive 25 to 30%. That's a huge deal. That's the kind of jump that makes all-day battery life a reality, even with heavy use. And hey, remember that leakage problem we were talking about? The villain of the story? With that gate-all-around iron grip, standby power leakage is cut by a whopping 75%. This directly attacks the single biggest weakness of the old FinFET design.
And on top of all of that, the new structure just allows for better packing. The N2 process gives us about a 15% increase in transistor density. That means designers can cram more features and more power into the exact same physical area.
But here's the thing, and this is really important. Having a revolutionary new transistor isn't actually enough on its own. To truly unlock all that potential, the entire philosophy of how we design chips had to change right along with it. This is where a new idea called DTCO comes in. See, in the old days, the factory that makes the chips would basically just create a rule book and hand it to the designers. Not anymore.
Now, they work together from day one, designing the chip and the factory process hand in hand, co-optimizing everything. To really get how this works, you need to know about something called standard cells. When you're building a chip with literally billions of transistors, you don't draw each one by hand. Instead, you use these pre-designed, pre-tested building blocks that perform basic logical functions.
Honestly, the best way to think of them is as super sophisticated Lego blocks. Chip designers have this huge library of these blocks, and they pick and choose the ones they need to build out a brand new processor.
Well, TSMC's new toolkit for this is called NanoFlex, and it gives designers an incredible new set of Lego blocks to play with. They have these short, compact blocks that are optimized for efficiency, and they have these tall, powerful blocks that are built for raw performance. And the best part? They can mix and match them right inside the same chip to get the perfect balance.
So when you combine this hardware revolution, the nanosheet transistor, with the design revolution of co-optimization, you get a result that's so much greater than the sum of its parts.
This right here is the winning formula for the N2 generation. It's a perfect three-part harmony. You've got the groundbreaking new transistor, you've got the collaborative design philosophy, and you've got the flexible toolkit that empowers designers to use it all to its absolute full potential.
And this teamwork pays off with some incredible results. We're seeing new types of wiring that are 55% more efficient, letting data just fly around the chip. Memory cells are being packed in tighter than ever before, and a new voltage system allows for this incredibly precise, fine-tuned power control, squeezing every last drop of performance from your battery. These are the details that create a truly next-gen chip.
Ultimately, this potent combination of brand new hardware and a brand new design philosophy is what keeps progress moving forward. It's the engine that lets us continue building technology that is faster, more efficient, and more powerful year after year after year.
So welcome to the world of microscopic traffic jams, because this is where the real fight for the future of computing is happening, deep inside the architecture of our most advanced processors.
Okay, so what are we actually talking about here? In the industry, it's called the back end of line, or BOL for short. I want you to imagine a bustling metropolis, but instead of skyscrapers, you've got up to 20 layers of incredibly intricate wiring, all packed into a space smaller than your fingernail. It is an absolute engineering marvel, but it's also become a logistical nightmare.
And here's where the real problem, the core conflict, kicks in. This 3D city of wires has to do two totally different, critical jobs at the same time. First, it has to be an information superhighway, routing data signals between billions of transistors. And second, at the exact same moment, it has to be the power grid, delivering electricity to all of them. The problem? Both of these vital networks are literally fighting for the same, incredibly limited physical space. It's a war for real estate on a microscopic scale.
And this intense fight for space, well, it leads to some truly catastrophic physical consequences. You see, this isn't just an engineering puzzle anymore. This is where the fundamental laws of physics start working directly against us, and with a vengeance. So the single most crucial point is this. To cram everything into that tiny footprint, engineers have no choice but to make the copper wires narrower and narrower. But basic physics tells us that when a wire gets thinner, its electrical resistance skyrockets. It's like trying to force a river through a garden hose. And that single fact is where everything starts to go horribly wrong.
And this shows you the two-front war that designers are losing. For the data wires, that high resistance creates signal delays. The chip literally slows down because transistors are just sitting around waiting for information to finally arrive. But for the power delivery wires, the problem is so much more destructive.
And that brings us to the main villain of our story, something called IR drop. It's a fundamental law of physics, you just can't get around it. As electricity pushes through those thin, high-resistance power wires, the voltage literally sags. By the time that power actually gets to the transistor, it's been weakened, starving the transistor of the juice it needs to switch quickly. It completely wipes out the benefits of having faster transistors in the first place, and, to add insult to injury, it generates a ton of performance-killing heat.
It's been described perfectly as a catastrophic traffic jam. The old way of doing things, the traditional front-side power network that has served us well for decades, has finally hit a hard physical wall. A total architectural redesign isn't just an option anymore. It's the only way forward. So how do you solve an impossible traffic jam? You don't just add another lane. No, you build a whole new highway system on the other side of the city.
The solution is as radical as it is brilliant. A backside power delivery network. I mean, the name says it all. Instead of fighting for space on the front of the chip, engineers are moving the entire power grid to the back.
Now, this is not just some minor tweak. This is like performing open-heart surgery on a microchip. First, you have to physically flip the entire silicon wafer over. Then you shave the back of it down until it's microscopically thin, just to expose the underside of the transistors. And only then can you start to build a brand new, super efficient power grid right there on that exposed backside. It's wild.
And hey, this isn't just a theory. The industry giant TSMC is bringing this to market with a technology that is set to be a complete game changer for high-performance computing.
Meet the A16 Super Power Rail. It's slated for mass production in the second half of 2026, and it's the ultimate solution to that traffic jam we were talking about. It completely decouples power and data. The front side of the chip is now dedicated only to data signals, while the back side becomes a clean, efficient, low-resistance power grid. The secret sauce is a new tech called nano TSVs, which are like microscopic elevators that deliver power directly from below, bypassing the gridlock on the front side entirely.
So just how difficult is this to manufacture? Get this. The alignment between the front of the wafer and that new power grid on the back has to be perfect, down to just 3 nanometers. For perspective, that's about the width of a few dozen atoms. The level of precision here is just staggering.
But what does all that incredible engineering actually get you? Well, an 8 to 10% speed boost might not sound like much, but in the world of AI and supercomputing, that is a massive leap forward. And by clearing out the power grid from the front, designers can now pack more transistors closer together. That's what logic density means. Basically, more brain power in the same tiny space. We're talking a boost of up to 10%.
And here's what might be even more important for a lot of our devices: power efficiency. If you run an A16 chip at the same speed as the previous generation, it uses 15 to 20% less power. In the real world, that means noticeably longer battery life for our phones and laptops, and much more efficient, cooler-running data centers. That's a huge win.
Okay, so the A16 node and its super power rail solved the wiring bottleneck in a really revolutionary way. But what comes next? Let's take a look at the technology roadmap to the end of the decade.
So here's the plan. We're currently in the era of the N2 node. Then, in 2026, the A16 node comes in and introduces that game-changing super power rail. But after that, in 2028, we get the A14 node, which represents the next major evolution of the transistors themselves.
Now here's where things get really fascinating from a strategy point of view. You'd think after developing this revolutionary superpower rail, they'd put it in everything, right? Well, wrong. The base version of the A14 node will actually go back to the traditional front-side power delivery, and there's a very, very smart reason why.
It's all about tailoring the tech to the right market. The base A14 is for things like our phones, our smartwatches, and other connected devices. Now, these applications will get a huge benefit from the new transistors, but they don't need the absolute bleeding-edge performance that requires the more complex and expensive backside power grid. But for the high-end clients in AI and data centers, don't worry. An enhanced A14P version will bring back the superpower rail around 2029 to deliver every last drop of performance. It's a brilliant strategy to optimize for both cost and power.
And don't think for a second that the base A14 is any kind of slouch. This huge leap is made possible by a new type of transistor architecture called a nanosheet, which is way more efficient and powerful than previous designs. This allows for a massive generational leap all on its own, up to 15% more speed, an incredible 30% reduction in power, and over a 20% density increase compared to the N2 node. The thing is an absolute beast.
Okay, so to really get our heads around their dilemma, we first need to understand the basic challenge of making computer chips today. I mean, we are trying to print electrical circuits with features that are now, well, they're smaller than a virus. Just think about that for a second. The way they do this is with a process called photolithography. Now, at its core, the idea is actually pretty simple. You use light to print a pattern onto a silicon wafer. Think of it like a projector, but instead of throwing a movie up on a screen, you're shrinking down and projecting a super complex circuit diagram onto the raw material of a chip. But, you know, there's a catch. When the things you need to print are that small, normal light just won't work. The wavelength is too big. So the industry had to invent a process that honestly sounds like it's straight out of science fiction: extreme ultraviolet lithography, or EUV for short. And this process is just wild. Okay, get this. It all happens inside a massive vacuum chamber.
A super high-power laser zaps a tiny microscopic droplet of molten tin, which vaporizes it instantly into a plasma. That plasma then lets out this intense flash of EUV light, which is then bounced off the most perfect, flattest mirrors ever made by humans to finally print the circuit. It's an absolutely incredible piece of engineering.
But you'd think that would be the end of the story, right? Nope. Even this sci-fi tech has its limits. As we try to make chips for our next phones, our next computers, we are hitting another hard physical wall. And the industry's fix for it, well, it's a pretty painful workaround. So here's the problem in a nutshell. The standard EUV machines that everyone uses today, they just can't print the tiniest, most cutting-edge patterns in one shot. That flash of light, as amazing as it is, just isn't sharp enough to draw the finest lines we need. So they came up with this clever, if a bit clunky solution called multi-patterning. The idea is you take one really complex chip design, you break it up into several simpler patterns, and then you print them one after another, layering them perfectly on top of each other. The best way to think about it is using a bunch of different stencils to create one super detailed final image. But this workaround, it's a nightmare. First off, it massively increases the number of steps and the time it takes to make just one wafer. But the worst part? It introduces this huge risk of error. If any one of those stencils is misaligned, and we're talking about being off by just a few atoms, the entire chip, worth millions, is completely worthless. So to finally get rid of this multi-patterning headache, the one company that makes these machines, ASML, has developed a truly revolutionary new tool. This is the real next-generation machine everyone's been waiting for. And here it is, the High-NA UV machine. Now, the magic number here is something called the numerical aperture, or NA. Just think of it as a measure of how sharp the image is. The old machine is 0.33. The new one, it jumps all the way to 0.55. That is a massive leap in power. And the promise of this new tech is beautifully simple. High-NA machines can print features that are almost twice as small, and they can do it in a single exposure, a single flash of light. This means you can just throw out that complex, risky, time-consuming multi-patterning process. It's a much simpler, faster way to make chips. It sounds perfect, right? I mean, this is the miracle fix the entire industry has been waiting for. Well, there's a twist. A pretty dramatic one, actually. This fix isn't quite as perfect as it looks. First, let's just talk about the price. A single one of these machines, which are about the size of a city bus, by the way, costs up to $400 million a piece. That is just a staggering amount of money. And you know what? The price isn't even the biggest problem. Because of the fundamental physics of how these new machines work, they create a brand new, very difficult technical challenge. It's called the stitching problem. So here's what's going on. Because of the new mirror design, the machine shrinks the circuit pattern, well, weirdly. It shrinks it 8 times in one direction, but only 4 times in the other. It's an optical quirk, and the result is that the total area it can print in one flash is cut in half compared to the older machines. So this creates a huge headache for chip designers. If your brand new $400 million machine can only print 1/2 of your chip design at a time, how do you build the whole thing? The only way is to print 1/2, then print the other half right next to it and stitch them together with perfect atomic level precision. And this is where our story really gets interesting. This technological crossroads, this hugely expensive machine that solves one massive problem but creates a totally new one, has forced the world's biggest chip makers to go in completely different directions. And here is the great divide, clear as day. On one side, you've got Intel, going all in on High-NA, betting they can be the tech leader again. And on the other side, you have TSMC, taking a much more pragmatic, cost-focused approach, deciding to stick with the older machines for now. Intel is basically betting the farm on this new technology. They've bought the very first machines, and they're betting their entire turnaround strategy on being the first to get them working. For them, it's an aggressive all-or-nothing play to leapfrog the competition and reclaim the crown as the undisputed technology leader. In total contrast, TSMC has looked at the numbers, done the math, and made a completely different calculation. They believe that even with all its headaches, sticking with the older machines and just getting better at that painful multi-patterning process is significantly more cost-efficient right now. And this chart right here is the simple economic logic behind TSMC's decision. Look, a single exposure on a High-NA tool costs roughly 2.5 times more than on a standard one. That means High-NA only starts to save you money if it's replacing 3 or more of those old multi-patterning steps. TSMC is betting they can design their chips to stay below that line. Now, to be perfectly clear, TSMC isn't saying no to High-NA forever. Not at all. They're just delaying it. They're pushing its adoption out to a future generation of chips, probably closer to 2030, when the technology is more mature and, hopefully, the costs make more sense. So to really get what's going on, you have to picture the inside of a computer chip. It is not just some flat piece of silicon, not at all. Think of it more like a sprawling 3D metropolis, a city with billions of transistors as the buildings, all connected by this incredibly complex network of wires. These are the superhighways, routing data all over the place. And for the last 3 decades, the undisputed king for building these superhighways has been copper. You know, when it was introduced back in the 90s, it was a massive, massive breakthrough. It let chips get faster and smaller year after year. It basically powered the entire tech boom we've all been living through. And that brings us to our first section, the end of copper's reign. We are literally watching the fall of a technology that's been the industry standard for an entire generation. The core of the problem is actually pretty simple. We've just pushed copper too far. As we build these wires at this insane scale, we're talking around 24 nanometers, which is something like 4,000 times thinner than a human hair. The fundamental physics of the element it can't keep up. It is literally breaking down at the atomic level. Which leads us right into the science behind this failure. Let's dig into the 2 really critical things that are causing this whole crisis. And trust me, this is where it gets really interesting. Okay, this slide right here shows the first major problem perfectly. See, you can't just slap pure copper into a chip. It would leak all over and cause a catastrophic short circuit. So you have to line the trench with this protective barrier layer. Now, in the old, bigger wires, this barrier was basically nothing. But look at today's tiny wires. That barrier takes up so much room, there's barely any space left for the actual copper. It's like building a 4-lane highway, but then only leaving 1 lane open for all the traffic. It just doesn't work. The second problem is a quantum thing called electron scattering. Imagine an electron is a sprinter trying to run down a hallway. In a nice, wide-open hallway, it's a straight shot, right? But as that wire narrows down to just a few atoms wide, that hallway gets incredibly crowded. The electron starts just violently bouncing off the walls, the wire's surfaces, and crashing into all these little obstacles, like the grain boundaries of the copper. All that chaos makes the electrical resistance just skyrocket, and it slows the whole chip down to a crawl. And believe it or not, it gets even worse. To push a signal through that super high-resistance wire, you need an intense electrical current, and that leads to this really destructive process called electromigration. The best way to think about it is to imagine the flow of electrons not as a gentle stream, but as a raging river. And this river is so powerful, it physically tears away copper atoms from the wire, just like a flood eroding a riverbank. And this shows you that deadly progression, that intense current, the river. It starts pushing atoms downstream. Over time, this creates these tiny, microscopic voids, little empty pockets in the wire. Eventually, one of those voids gets so big that it completely severs the wire. And when that happens, the whole chip fails, permanently. Game over. So, with copper failing this spectacularly, what's the solution? Well, this brings us to the most exciting part of the story, the hunt for new miracle materials to save the future of computing. So here we go, let's put them head to head. On one side, you've got the old champion, copper, and on the other, 2 new challengers from the periodic table, ruthenium and cobalt. Now, at first glance, they might just seem like different metals, but look closer. Their resistance to that destructive electromigration we just talked about, it's way, way better. And crucially, at these tiny dimensions, their unique atomic properties mean they actually have lower electrical resistance than copper. They just perform better when the hallways get this narrow. And one of these materials, ruthenium, really stands out. It's being called a miracle material for one very specific, very important reason. It doesn't need that thick, resistive barrier layer that was choking the copper wires. You can just fill the entire trench with pure, highly conductive ruthenium. That's like turning that 1-lane highway back into a full-blown superhighway. It solves one of the biggest problems in one single, elegant move. And get this,
While ruthenium and cobalt are busy solving the wiring crisis, researchers are already looking even further ahead. They're exploring radical new materials to replace silicon itself. I mean, we are talking about stuff that sounds like it's straight out of science fiction. Atom-thin, two-dimensional sheets of molybdenum disulfide, exotic oxide semiconductors, even one-dimensional carbon nanotubes. This is the stuff that's going to fuel computing deep into the 2030s and beyond.
But all of this incredible science, it comes at a price, a truly mind-boggling price. This innovation isn't just a triumph of physics, it is an exercise in some pretty extreme economics.
To put this into perspective, let's just start with right now. A single processed 12-inch wafer, using the most advanced tech available today, is estimated to cost around $30,000. That is for one single disk of silicon. And that's before it's even been cut up into individual chips. Okay, now to build the factories, the fabs, that can even handle these new Angstrom-era materials, well, the leading manufacturer, TSMC, is reportedly preparing an investment of $49 billion. Not million, billion. That is the kind of capital you need just to build the infrastructure for this next generation. And of course, to make back that astronomical investment, the cost per wafer is set to just explode. Industry analysts are projecting that by the time these new chips are out commercially, around 2028, the cost for a single next-gen wafer is going to surge to an astonishing $45,000. That's a 50% increase in just a few short years. And as you can see here, this isn't a one-time jump. It is a steep, relentless climb. For decades, the whole point was that the cost per transistor went down. That's what made technology more powerful and accessible for all of us. Well, that trend is over. We are now on an exponential cost curve, and it's going in the other direction. And the unavoidable consequence of all this is that the financial barrier to entry has become, well, insurmountable for almost everyone. At $45,000 a wafer, only the absolute wealthiest tech titans, the giant smartphone makers, the big AI data center companies, the dominant GPU designers, only they can afford to play at the cutting edge. Okay, so when your starting material is that expensive and that easy to break, your first job, your only job really, is to just not fail. And that brings us to the first huge economic battle in chipmaking. It's all about winning the yield game. And this right here, this is the most critical metric in the whole industry. It's called manufacturing yield. All it means is what percentage of chips on that wafer actually work perfectly. If you get a high percentage, you're making money. If you don't, well, you've just flushed a fortune down the drain. Now, as you can see, this is not an even playing field. Not at all. These are the estimates for the next-gen 2-nanometer chips. And there is a clear leader. You've got TSMC sitting pretty at around 65% yield, while its competitors are really struggling to even get close. So, how? How did they get so far ahead?
Well, it's not luck, it comes down to their business model. See, TSMC is a foundry, which means they make chips for tons of different companies. Apple, Nvidia, you name it. All that volume and variety gives them a massive amount of data. It creates this powerful feedback loop where they can spot and fix these tiny little flaws way, way faster than anyone else. All right, so let's say you've won that first battle. Your yield is solid, you're making chips that work, awesome. But immediately, a brand new problem pops up. Now you have to fight the war on wasted space. And this quote it nails it. Every single square millimeter of that $45,000 wafer is prime real estate. Any microscopic bit you don't use is like literally setting a pile of cash on fire. The goal here is total efficiency. The way you do that is with a strategy called design technology co-optimization. I know, it's a mouthful. Just think of it as playing a perfect game of Tetris, but at an atomic scale. It's about making sure the chip's design and the manufacturing process fit together perfectly, so everything is packed as tightly as humanly possible. This is where the chip designers and the factory engineers have to work together in perfect harmony. They use these incredible tools to meticulously cram in the logic gates. Those are the tiny on-off switches that do all the thinking, to squeeze every last drop of performance out of every dollar they spent on that silicon. So, just when you think you figured out the money problems, you run headfirst into a brick wall. The final, most intimidating barrier of all, the actual laws of physics. This is the ultimate battle.
I absolutely love this quote because it really gets at the scale of this thing. We're not just talking about making stuff a little bit smaller anymore. This is a calculated, multi-front war against the universe itself, just trying to keep Moore's Law alive. And this roadmap kind of shows you the battle plan. Over the next few years, each new generation of chip isn't just a general improvement. It's a specific solution to a specific fundamental physics problem. It's a step-by-step assault on what seems impossible. So first up in 2025, we have the N2 node. The problem? When transistors get this small, the electrons that are supposed to flow through them start to, well, leak out. It wastes a ton of power and generates so much heat the chip could literally cook itself to death.
And the solution is just brilliant. It's a complete redesign of the transistor. It's called gate-all-around, and it does exactly what it sounds like. It wraps the control gate completely around the channel the electricity flows through. This gives engineers total control, stopping the leaks and saving massive amounts of power.
But, of course, you solve one problem and a new one shows up. Fast forward to the A16 generation. Now you've packed so many of those new transistors together that the wiring on top of the chip becomes a total disaster, a catastrophic traffic jam. It creates these bottlenecks that starve the chip of power and slow everything down. The fix for this is just so clever. It's called the superpower rail. Basically, they move the entire electrical grid from the front of the chip to the back. Think about it like taking all the plumbing and wiring out of a skyscraper's walls and sticking it all in the basement. It frees up an incredible amount of super valuable space up top.
And that brings us to the A14 node. And here, we've come full circle. The problem isn't physics anymore, it's back to economics. The next generation of machines you need to build these chips, they're so astronomically expensive and so new and unproven that buying them could literally bankrupt you. So what's the answer? It's a really smart, pragmatic one. Instead of betting the farm on these crazy expensive new machines, the plan is to just get more creative with the tools they already have. They'll use clever engineering tricks to squeeze more performance out of the proven, reliable stuff. It's a business decision, not just an engineering one.
So after all that, what's the big takeaway? What is the real secret sauce here that's going to secure the future of computing for the next 10 years?
Well, it's not just one thing. It's not one magic bullet invention. The real winning formula is the deep, relentless integration of both manufacturing perfection, that's your yield, and brilliant optimized design, that's your DTCO. The two have to evolve together, hand in hand.
Okay, so if shrinking is off the table, what's next? Where do we go from here? To really get the answer, we have to pull back the curtain on how chips are actually made. And it's really a story of two different worlds. You got the famous front end, and then you've got the back end, which is kind of the unsung hero of this whole process.
The best way to think about it is like building a city. The front end, that's your star architect. They use mind-bending physics to sketch out this impossibly complex, microscopic city right onto a silicon wafer. But here's the thing. That beautiful city is useless. It has no roads, no power grid, no plumbing. That's where the back end comes in. They're the builders, the engineers who turn that amazing blueprint into a living, working city that can actually do something.
And for decades, let's be honest, the back end was kind of the boring part. It was seen as the grunt work, you know? Slicing up the silicon, connecting some wires, and sealing the whole thing in a protective plastic case. It was absolutely critical work, but all the glory, all the big R&D money, that always went to the architects on the front end.
But now, that whole dynamic has been flipped completely on its head. Since we can't really shrink the transistors anymore, the entire job of making things faster has fallen on the shoulders of the back end. Packaging isn't just about protecting the chip anymore, packaging is the performance.
This is the new game. It's called advanced packaging, and it's all about taking a bunch of different specialized chips and stitching them together so tightly that they act like one single massive supercomputer. The package itself has become the superhighway that connects everything.
And the company that's really leading the charge here is TSMC, with this whole ecosystem they call 3D Fabric. It isn't just one single technology. Think of it as a whole toolbox full of ways to stack silicon in 3 dimensions, all of it designed specifically for the absolutely insane demands of AI and high-performance computing.
So how does this actually work? Well, the idea at the heart of 3D Fabric is actually really elegant and, frankly, genius. It's all about modularity. Forget trying to build one single, gigantic, flawless chip. Instead, think of it like building with Legos. Very, very advanced Legos.
And these little Lego blocks have a name. They're called chiplets.
A chiplet is just a small piece of silicon that does one thing really, really well. So you might have a chiplet for processing, another for memory, another for communications. You design each little block on its own, and then you just click them together to build a much more complex system.
And the advantages of this approach are just massive. See, when you make one giant chip, if there's one tiny little flaw anywhere, you have to throw the whole thing out. What a waste! With chiplets, if one little block is bad, you just toss that one out. It also lets you mix and match. You can use the absolute latest, most expensive tech for the parts that need the speed, and then use older, cheaper, proven tech for everything else. It's cheaper, it's faster to design, and it's so much more flexible.
But look, this isn't something one company can just decide to do on its own. Stacking chips isn't like stacking pancakes. It is incredibly complex. To actually pull this off, you need the entire industry to get on the same page and work together in a totally new way.
I mean, just think about the physics for a second. When you stack a dozen high-powered chips on top of each other, how do you get heat out of the chip in the middle? How do you even get power to it? How do you keep billions of electrical signals from getting all jumbled up? These are huge, huge engineering puzzles.
So to solve this, TSMC created something called the 3D Fabric Alliance. It's basically a big team that gets everyone in the same room. The software companies making the design tools, the memory makers, the testing specialists, everyone. The whole point is to make sure that every single piece of this complicated puzzle fits together perfectly, right from day one. And one of the coolest things to come out of this is a standard called 3D blocks. Before, you had all these different design programs that just couldn't talk to each other. The software for figuring out heat couldn't communicate with the software for figuring out the physical layout. It was a mess. 3D blocks acts like a universal translator. It's a common language that lets all these different tools finally work together as a team.
And this brings us to the last part of the story, and this is where things get really wild. We just talked about how incredibly complex this all is, so how do you even manage it? Well, you use the very same technology that you're trying to build.
So today, the design tools that engineers use are infused with artificial intelligence. These AIs can automatically explore thousands, even millions, of different design possibilities, figuring out that perfect, delicate dance between heat and power and signaling across all those stacked layers, a job that would be nearly impossible for a human brain to do. So you end up with this stunning feedback loop. We are now, and this is a quote, effectively utilizing artificial intelligence to design the very hardware that will run future artificial intelligence applications. It's AI building the foundation for the next generation of AI.
Now, to really get why this packaging is so ridiculously important, we need to talk about the fundamental problem that modern AI is up against. And it's basically a problem of microscopic traffic jams. The source material puts it perfectly. These processors are just starving for data. I mean, they can process information way, way faster than we can actually feed it to them. The whole challenge is just getting insane amounts of data from the memory to the processor in basically no time at all. And the solution to this data starvation problem is a little thing called an interposer. The best way to think of it is as a tiny, super advanced circuit board. It's like a data superhighway that lets the processor and all its memory talk to each other at unbelievable speeds. This thing is the key to the whole operation. Okay, so here's how it all fits together in what we call a CoWoS package, and that just stands for chip-on-wafer on substrate. First, you've got the foundation, the substrate, which is what connects to the motherboard. Then, on top of that, you mount the interposer, our data bridge. And finally, you place the payload, your main logic chip and stacks of high bandwidth memory, right on top of that bridge, getting them as close together as physics will allow. Now, the very first crack at solving this, the most established method, was just an all-out performance play. It's a version called CoWoS, and it relies on the absolute best, purest material they have in the world of semiconductors. Right, so the S in CoWoS, that stands for silicon. This approach uses a huge interposer made out of pure silicon, the exact same stuff that chips are made of. Why? Because it lets you create unbelievably dense microscopic wiring. You get an information superhighway with just massive data bandwidth and absolutely perfect signal integrity. For pure performance, this is the gold standard. But there's a huge catch with this gold standard. There's a fundamental physical limit in making chips, and it's called the reticle limit. Basically, the machines that print circuits onto silicon can only print a rectangle of a certain maximum size in one go. And the problem is, these AI packages need to be way, way bigger than that. So to get around this, what they have to do is stitch multiple prints together, sometimes more than 3 times the size of a single reticle. As you can imagine, this is incredibly difficult, it's super expensive, and if even one tiny flaw happens anywhere in that process, the entire, very costly package is trash.
This whole problem of cost and fragility, it just screamed for a new, smarter solution. And that brings us to CoWoS-R, the next evolution in this story, which was designed to tackle those exact issues. Okay, so instead of that rigid, fragile silicon interposer, CoWoS-R, and the R here stands for redistribution layer, it uses a flexible organic polymer. So what's the trade-off? You give up a little bit of that absolute top-of-the-line performance, but you get a massive boost in reliability and a much, much lower cost. So why is being flexible so important here? Well, it all comes down to basic physics. When these giant AI packages are running, they get incredibly hot. And all the different materials, the silicon, the memory, the substrate, they all expand and contract at different rates. And that mismatch creates enormous mechanical stress. Think about pouring hot water into a cold glass, and it cracks. Same idea.
And this is where CoWoS-R is just genius. That flexible organic layer, it acts like a shock absorber. It just soaks up all that thermal stress, stopping things from warping or cracking. This makes a huge difference in how many of them actually work off the production line and how long they last, which makes it perfect for things like big networking gear.
Okay, so we've got maximum performance with CoWoS, and we've got cost-effective reliability with CoWoS-R. But you know what engineers always ask, right? Can we have both? Can we get the best of both worlds? Well, that is the whole idea behind the latest, most advanced version, CoWoS-L. And the goal here is not a small one. The ambition for CoWoS-L is to completely shatter those reticle size limits that were holding back the silicon version while still delivering that same insane level of performance. So how on earth does it work? It's a really masterful hybrid. The L stands for Local Silicon Interconnect. You start with that big, cheap, and reliable organic base, just like CoWoS-R. But then, you embed these tiny, super targeted silicon bridges only where you absolutely need that ultra-dense wiring, right between the main processor and the memory. It's brilliant. You get the scale and reliability of the organic base with the pinpoint performance of silicon exactly where it counts. And this hybrid approach, well, it just completely changes the game. And the roadmap for this technology, it is simply staggering. It is setting the absolute ceiling for what AI infrastructure can even become. First, let's just talk about sheer scale. Future CoWoS-LW packages are projected to get bigger than 3,000 square millimeters. I mean, to put that in perspective, that is larger than 2 credit cards sitting side by side. We are talking about absolutely gargantuan chip packages. Remember that old reticle limit we talked about? That hard physical wall they kept running into? By 2027, the plan is to be mass producing a package that is 9.5 times the size of that original limit. It's just completely blowing the doors off the old constraints. And what does all that extra space get you? It lets you integrate 12 or even more separate stacks of next-gen high-bandwidth memory right next to the processor. That original data starvation problem, this is how you engineer it out of existence. So, at the end of the day, here's what you need to take away from this. This is not just some minor technical update. This ability to scale is a strategic triumph. It is setting the physical limits for what the next generation of trillion-parameter AI models can even dream of being. You see, the demand for these high-performance processors just exploded, seemingly overnight. It caught the entire global supply chain completely off guard. But the real choke point, the real problem, wasn't where anyone expected it to be. So, what was it? And the answer, honestly, it might surprise you. The problem wasn't actually making the silicon wafers themselves, the front-end manufacturing that gets all the headlines. Nope. The real bottleneck, the hidden constraint, was in the final assembly. So to really get how this happened, we've got to unpack the problem a little. The world just didn't have the specialized capacity to assemble these new, incredibly complex AI processors at the massive scale the market was suddenly demanding. This brings us to the absolute core of the issue: advanced packaging. Now, this isn't just about sticking a chip in a little plastic case. Oh no, we're talking about a mind-bogglingly complex process. It's about integrating multiple tiny, powerful components into one single, cohesive superprocessor. And this became the single limiting factor in the entire AI hardware boom.
So this distinction right here is absolutely crucial. The world's most advanced foundries, they could make the logic chips. That's the front-end fabrication. But the back-end process, the actual assembly of the final product, that's where the entire system just ground to a halt. This kicked off an aggressive, unprecedented, and incredibly well-funded race to build more capacity. And when I say race, I mean it. We're talking about a numbers game on an unbelievable scale.
So before the whole generative AI thing just exploded, the industry was kind of comfortably producing around 75,000 of these advanced packages every month.
That was the baseline. That was the world's total capacity.
But suddenly, with customers just demanding more and more and more, the new target became a run rate of 130,000 wafers per month. Just think about that for a second. The industry needed to nearly double its entire global output, and they needed to do it like yesterday. The scale of this challenge was just immense. I mean, this wasn't some minor adjustment. It was a massive industrial scale ramp up that had never, ever been attempted before at this kind of speed. So how on earth did they pull it off? Well, how do you solve a problem this big? It really starts with the tools. You can't build the packages if you can't first build the machines that build the packages. And here's the key advantage the industry had going for it. You see, unlike front-end chip making, which is totally dominated by a few monopolies with these hyper-expensive, massive EUV machines, the equipment for back-end packaging actually has lower barriers to entry. And what that meant was that new players could step up to meet the insane demand. And we are not talking about simple equipment here. To build just one of these packages, you need a factory that is filled with hundreds of highly specialized machines. I'm talking electroplaters for doing intricate wiring, die bonders for placing chips with micrometer accuracy, molding machines, grinders, specialized ovens. It is a symphony of high-tech manufacturing. And a robust, localized supply chain, especially in Taiwan, became the strategic weapon here. Local equipment suppliers, who had decades of expertise, could rapidly fill these massive orders without the painful delays of overseas shipping, which was just absolutely critical. So that brings us to the second part of the solution, speed. The industry wasn't just building, it was literally racing against the clock, at a pace that just completely upended traditional timelines. The timeline really tells the whole story. A typical facility expansion used to be planned over 7 quarters. That's almost 2 years. Because of the AI boom, that entire process, from designing the factory to mass production, got compressed into just 3 quarters. Incredible. Now, to achieve this kind of speed, they used a 2-pronged strategy. First, rapid retrofitting, basically taking over old factories like LCD plants and quickly converting them. And second, building entirely new mega facilities from scratch with massive new plants planned everywhere from Taiwan all the way to Arizona. But you know what? Even with new machines and super fast construction, one company couldn't do it alone. The final piece of this puzzle was a radical reshaping of the industry itself, all through the power of partnership. The sheer volume of orders was pushing the world's main foundry to its absolute limits. I mean, to keep from breaking, and to focus on the most complex and profitable stuff, it had to do something pretty unprecedented. It had to strategically outsource parts of the process. And this created a whole new ecosystem. So you've got the primary foundry focusing only on the hardest jobs. Then its trusted partners, known as OSATs, which just stands for Outsourced Semiconductor Assembly and Test Companies, they took on the simpler tasks and massively expanded their own production lines with plans to triple their capacity. All the while, the equipment suppliers were just feeding the machines to everyone to fuel this expansion. So ultimately, this whole capacity build-out wasn't just one company getting bigger, it was a massive collaborative effort, creating a broader, more resilient supply chain that could finally handle the relentless global demand from a bunch of different angles. So, what are the key takeaways from all this? Well, first, the real AI bottleneck was in the unglamorous, but totally critical, world of packaging. Second, the solution was a truly historic industrial ramp-up at absolute breakneck speed. And finally, and maybe most importantly, it was only possible through a combination of localized supply chains and really unprecedented collaboration across the entire industry.
All right, today we're talking about going vertical and what it means for the future of computer chips. And trust me, this is a much bigger deal than it might sound.
So let me ask you a quick question. What do you think modern data centers and, say, the most crowded cities in the world really have in common?
Well, the answer is surprisingly simple. They're both running out of space.
I mean literally. And for computer chips, just like for our big cities, the only way to grow anymore is up. That flat, two-dimensional footprint has become a massive, massive bottleneck. Okay, so if you can't build out, you've got to build up, right? And this is where the whole idea of building silicon skyscrapers really comes into play.
Now, the first stab at this was a technology called microbumps. Just think of them as these tiny, microscopic balls of solder. They were basically the rivets holding the different floors of our silicon skyscraper together.
But yeah, this old way, it had some fatal flaws. For one, the microbumps themselves were actually kind of big, which really limited how many connections you could cram in there. But the real killer was a process called electromigration. The intense flow of electricity would literally just shove metal atoms out of place, creating these tiny little cracks. And eventually, poof, the circuit breaks, the chip dies. Game over.
So yeah, that was not going to cut it for the future of high-performance computing. To get past these huge physical limits, engineers needed something totally different, something that was, almost like magic.
This incredible new tech is called hybrid bonding, and it's a total game changer because it completely gets rid of the solder. It's a bumpless technique that, get this, literally fuses copper pads together at an atomic level. It's really less like construction and way more like chemistry.
So how does this atomic magic actually work? Well, it's an absolute masterclass in precision. First, they take the two chip surfaces and polish them to a smoothness that's just, honestly, it's hard to even imagine. We're talking fractions of a nanometer. And this is so critical because any little bump, even one atom high, would ruin the whole thing. Then, check this out. At room temperature, the insulator parts of the surfaces just fuse, instantly, on contact. And for the final step, they apply a little bit of heat. This makes the copper pads swell up and fuse together, again, at the atomic level, creating thousands of perfect connections all at once. It's wild.
Okay, so this process is obviously incredible, but trying to do it perfectly millions and millions of times, well, that introduces two brand new, really tough enemies, dust and heat.
And the problem with dust, it is catastrophic. I love this analogy. It illustrates it perfectly. It says a single microscopic particle can act like a tent pole, creating a void around it that prevents thousands of connections from touching, ruining the entire chip. Think about that. Just one tiny speck of dust and the entire expensive chip is completely worthless. So, as you can imagine, the solution has to be pretty extreme. Manufacturers have to use some of the cleanest places on the entire planet. We're talking ISO Class 3 clean rooms. I mean, the air in there has thousands of times fewer particles than a hospital operating room. And to cut the silicon wafers, they can't use saws anymore. That makes dust. So instead, they use these advanced plasma beams to just slice right through it.
Okay, so that handles the dust. But what about the heat from the bonding process itself? Too much heat is just going to fry the delicate transistors that are already on the chip. To solve this, material scientists came up with something called nano-twinned copper. It's this really special material that allows that final atomic fusion to happen at around 200 degrees Celsius instead of the usual 400. And that difference is an absolute game changer. It's what keeps the whole thing from melting.
So mission accomplished, right? We've built our silicon skyscraper. But in solving one problem, we've created a brand new, almost existential crisis. We are now hitting the thermal wall.
See, by stacking all these processors, we've concentrated an absolutely insane amount of power into a tiny space. We're talking power densities of 4.8 watts per square millimeter. To give you some perspective on that, that's a heat intensity that's actually getting close to the surface of the sun. It is a mind-boggling amount of energy.
And therein lies the problem. The sheer volume of heat is it's too much. Your standard air cooling, fans, even the traditional liquid cooling systems we've had for years, they've all failed. They just can't keep up. Not even close.
So what on earth is the answer? Well, it's simple in concept, but crazy in execution. If you can't cool the chip from the outside anymore, you have to find a way to cool it from the inside.
And you can see the fundamental difference right here. Conventional cooling, right, it uses that thermal paste to connect a cold plate to the chip. But that paste, it actually acts like a tiny little blanket, trapping a layer of heat. Direct-to-silicon cooling just throws that blanket away entirely by embedding the plumbing, the actual cooling channels, right into the silicon itself.
And how it works is just a marvel of fluid dynamics. I mean, they build these microscopic fluid channels directly into the chip. And inside those tiny channels, they engineer these little pillars and trenches, all designed to do one thing: disrupt the water flow. This creates a state of turbulent flow, which is key.
That turbulence forces way more of the water into direct contact with the hot silicon, and it just yanks the heat away with incredible efficiency.
And the results are just staggering. This new technology can cool a single chip that's continuously pulling over 2.6 kilowatts of power. That is enough energy to run a high-end air conditioner, and it's all concentrated in a space that's smaller than the palm of your hand.
So what does this all add up to, really? Look, this isn't just about a better chip or a better cooler. What we're witnessing here is the profound convergence of two completely different scientific fields: semiconductor fabrication and advanced fluid dynamics. They had to come together to break a fundamental barrier in physics.
And here's the crazy part. For decades, this is how we've done it. We create hundreds of processors on these big, beautiful circular silicon wafers. And then, what do? We take a diamond saw and we dice it all up into tiny individual chips. We package them up, stick them on circuit boards, and then spend a massive amount of time and effort wiring them all back together. We literally create the problem ourselves. What if you took this huge problem and came at it with a solution that's so simple it's almost absurd?
The idea, really, is as simple as it is brilliant. Just abandon the dicing process entirely. That's it. Instead of cutting all those chips apart just to wire them back together, you leave them connected, right there on the original, uncut piece of silicon. And this concept has a name: System-on-Wafer, or SOW for short. And it is a monumental shift in thinking. You're turning an entire 12-inch wafer into one single, gigantic, unbroken processor. The data never has to leave that super-efficient silicon highway. The bottleneck doesn't just get smaller, it's completely erased. Now, this isn't just some cool theory on a whiteboard. This is very real. And the most powerful example of it out there is the Cerebras Wafer Scale Engine 3, or WSE3. And it is an absolute beast, a true masterclass in what it takes to pull something like this off.
Let's just talk about the scale here for a second. Get ready for this. The WSE3 packs 4 trillion transistors. No, that's not a typo. 4 trillion.
On that single piece of silicon, it integrates 900,000 individual cores, all of them specifically optimized for doing AI work. And the payoff for keeping everything on that one wafer, a mind-boggling 21 times petabytes per second of memory bandwidth. The speed is so fast, it's almost hard to even wrap your head around.
Okay, let's put those numbers into perspective, because they're just huge. A traditional high-end system might have a few thousand cores. The WSE3 has 900,000. You might have megabytes of fast memory on a chip. This has 44 gigabytes. You talk about terabytes of bandwidth. This thing has petabytes. We're not talking about an incremental improvement here. This is a whole different ballgame. But as you can probably imagine, when you try to build something this revolutionary, you run into problems that, well, nobody has ever had to solve before. The engineering hurdles are just monumental.
And here is the biggest, most obvious one, right? It is practically impossible to make a perfect 12-inch wafer. There's always going to be tiny defects. Normally, one microscopic flaw means you toss the chip. So how on earth can this possibly work if the whole thing is one chip?
The solution is just so clever. Basically, the system is built to expect failure. It runs a test on the whole wafer, it maps out every single defect, and then it uses a whole network of built-in, redundant connections to automatically and silently just route around any of the dead cores. So to the software running on top, it just sees a perfect, flawless computing grid. Problem solved. Okay, so you fix the hardware. Check. But that just opens up a whole new can of worms on the software side. I mean, how do you even begin to program a processor that's this big? Data is going to take longer to get from one side to the other, and managing all that is a huge, huge challenge. You can't use the old ways. You need a totally new programming model, rebuilt from the ground up. The software is designed to handle those different travel times across the wafer, using really sophisticated routing to avoid data traffic jams. And the result of all this incredibly complex work, it can run a large language model inference in under a single millisecond, a speed that is physically impossible for a conventional system to achieve. So here's the crucial takeaway. This whole thing isn't just a one-off product. The WSE3 is really just the beginning. It's the proof of concept, the foundation for what's coming next in computing.
And there's already a roadmap laid out, We've got the WSC3 today, and on the horizon, scheduled for 2027, is the next generation platform, which is codenamed SOX.
And SOX is where things get even crazier. The plan is to integrate not just the computer cores, but also external memory and even the optical networking hardware directly onto the wafer. It's not just a processor anymore, it becomes a fully self-contained supercomputer on a single slice of silicon. The performance gain they're estimating is just hard to believe. They're projecting 40 times, 40, greater computational power than the most advanced multi-chip systems we have today. A 40x leap is just staggering.
And why does any of this matter? Because this is the kind of horsepower that's going to be absolutely necessary for the AI models of the near future. We're talking models with not just billions, but many trillions of parameters. This tech is being purpose-built for a future that we can all see coming.
All right, so if electrons in copper have hit their limit, what's the answer? Well, this is where we see this beautiful fundamental shift in thinking. A solution that's literally made of light. We're moving from the world of electrons to the world of photons.
And the hero of our story is a technology called silicon photonics. And honestly, it's as elegant as it sounds. Instead of pushing electrons through a wire, you're using these rapid little pulses of laser light, photons, to send digital data zipping through microscopic glass fibers, all of it built on a standard silicon chip.
And this is why it's such a game changer. I mean, look at this comparison, it's just night and day. Where copper guzzles energy, fiber just sips a tiny fraction. Copper generates tons of heat, fiber generates none. Signal loss is a huge problem in copper, it's extremely low in fiber, and the bottom line, you get vastly, vastly higher bandwidth. Photons just don't play by the same restrictive rules that electrons do. But here's the thing, just switching to light isn't the whole story. The real genius is in how you integrate it, and that brings us to what's being called the vertical revolution and a breakthrough technology known as COUPE. Okay, so this whole system is called COUPE, which stands for Compact Universal Photonic Engine, and it's designed to bring these two different worlds together perfectly. You've basically got two key parts. First, there's the Photonic Integrated Circuit, or PIC. That's the part that handles the light, using these tiny little silicon rings to flick a laser on and off billions of times a second to encode data. Then you've got the Electronic Integrated Circuit, the EIC, which is the traditional digital brain that's running the whole show. So the big question is, how do you connect them? In the older designs, they just put these two chips next to each other. But this creates a fatal flaw. You still need a short little copper wire to connect them, which immediately brings back the exact same problems of electrical latency and power loss that you were trying to get rid of in the first place.
And here is the COUPE solution. It's absolutely revolutionary. Instead of putting the chips side by side, they went vertical. They stacked the electronic chip right on top of the photonic chip. Then they use these incredibly precise copper-to-copper connections to bond them, and they route the signals vertically, straight through the stack. It's really a masterpiece of 3D engineering.
So what does this get you? The result is profound. The electrical path is shortened from millimeters all the way down to just a few micrometers. We're talking the absolute physical minimum. This completely wipes out that parasitic signal loss and just drastically improves the overall energy efficiency. It's really the perfect marriage of electronics and optics. And, there's another huge benefit here. The COUPE engine is built like a solid block, almost like a single piece. So unlike older, more fragile designs, this thing is super robust. And that results in what's called exceptionally low optical insertion loss, which is really just a fancy way of saying that very, very little light gets wasted. Every single photon counts.
Okay, so we get how it works. Now, what does it all mean for the future? This is where things get really exciting. Let's talk about the co-packaged future and how this is all going to unleash AI's true potential.
So here's the game plan, and it's pretty ambitious. First, in 2025, we're going to see pluggable modules. These will give an immediate performance and energy boost to the data centers we already have. But the real industry-shaking moment, that's scheduled for 2026, and that's the arrival of co-packaged optics. And this is the monumental leap. Co-packaged optics basically means shrinking that entire optical engine down and putting it inside the exact same package as the main processor. Think about it like this. It's like moving the fiber optic port from the wall and putting it directly on the CPU itself. You get the massive bandwidth of fiber optics straight into the heart of the chip, and you completely eliminate the need for those power-hungry electrical signals running across the motherboard. The speeds we're talking about are just, well, they're staggering. To put it in perspective, future versions of this platform are already aiming for an incredible 6.4 terabits per second. That is enough bandwidth to download hundreds of high-def movies in a single second. And it doesn't stop there. The very next generation is already targeting double that, 12.8 terabits per second. This isn't just about faster downloads for you and me. These are the colossal speeds that are going to be required to feed the next wave of truly advanced AI. Which brings us right to the end goal, the whole point of all this innovation. It's about tearing down that input/output bottleneck. The one thing that is currently starving our most advanced multi-million-dollar AI chips of the one thing they crave, a constant, massive fire hose of data. All right, let's get right into it. You know, the biggest revolution happening in computing right now, it isn't about just making things a little bit faster. Not at all. We are talking about a complete, fundamental teardown and rebuild of how high-performance computers are even designed. So here's our game plan. We're going to start with the end of the old way, then look at the new alliance that's making all this happen. After that, we'll dive into how this new world is being built, the barriers it's absolutely shattering, and finally, what kind of future it's going to power. You know, to really get where we're going, you have to understand what we're leaving behind. And make no mistake, we are standing at a huge turning point. We're literally witnessing the end of an idea that has dominated computing for 50 years. And this quote just says it all, doesn't it? This isn't some minor upgrade. To put it bluntly, the old king of computing, the monolithic processor, is dead. Its reign is over, and a totally new kind of three-dimensional system is rising up to take the throne. This slide lays it out perfectly. For decades, we had the monolithic processor. Think of it like a giant single-story factory, trying to do every single job under one massive roof. The new way, well, that's a high-tech skyscraper. It's a 3D system with specialized floors, or chiplets, all stacked on top of each other, each one doing its one job with incredible speed and efficiency. So, a revolution this huge? How does it even happen? Well, it's not the work of one single company. Nope. This is being forged through what our source material calls extreme, unprecedented collaboration across the entire tech industry. Just think about that for a second. For years, the memory companies, the processor logic companies, and the companies that assembled everything, they all worked in their own separate worlds. But they hit a wall, a physical wall. Making chips smaller and faster just got way too hard and expensive. To break through it, those old boundaries, they just had to dissolve. It's a massive shift, and it was born out of pure necessity. And this right here, this shows you the new power structure. It's a three-way partnership. The product designers, the memory makers, and the logic foundries are now working hand in glove from day one. They're all co-designing the final chip together as a team. And hey, this isn't just some theory on a whiteboard. Let's look at the next generation of high-bandwidth memory, HBM4. For the very first time, the memory companies are teaming up directly with the logic foundries to build that critical base die. That's the brain at the bottom of the memory stack on super advanced 5 and 12 nanometer tech. This is what lets the memory talk to the processor almost instantly. Okay, so we know who is building these new systems. Now let's get into the how. How are they physically constructing these incredible three-dimensional computing structures? We just mentioned that base die, and it's a term you're going to want to remember. It's not just a foundation, it's more like the super intelligent traffic cop for that whole memory skyscraper, managing an absolute torrent of data that's flowing up and down the stack at unbelievable speeds. And the engineering behind this is, well, it's just mind-blowing. They're literally building these systems in every direction at once. They're going vertical, stacking chips with insane density, bonding them at an almost atomic level. They're going outwards, connecting dozens of these chiplets on huge silicon foundations. They're even building power delivery and optics. I'm talking about using light instead of wires directly into the package itself. So we have this amazing new architecture built by a new kind of super team. But what does it actually do? What's the point? Well, simply put, it breaks the old rules that were holding computing back for years. First, let's talk about going wide. The source uses this fantastic term, reticle busting interposers. Now, what on earth does that mean? Well, a reticle is kind of like the stencil or the cookie cutter they use to print a chip. Reticle busting means they are now building single foundational chips that are bigger than the tools were ever designed to make. This lets them connect dozens and dozens of components right next to each other. And at the same time they're going wider, they're stacking higher with that incredible density. New ways of bonding these layers together mean the connections are so small and so perfect that data can just flow between them with almost zero resistance. It's like a superhighway for information. So what's the end game here? Where's this all heading? Well, it's the dream of a system-on-wafer. Imagine taking an entire supercomputer, the processor, the memory, all of it, and building it on one single seamless piece of silicon. This would completely get rid of those slow, green motherboards we're all used to seeing inside our computers. And the result of all this is truly profound. It permanently smashes the two great walls of computing, the bandwidth barrier, which is how much data you can move, and the energy barrier, which is how much power it takes to do it. This new 3D world is just massively more capable and way more efficient. So, at the end of the day, why does any of this microscopic world of silicon and copper even matter to us? How does this invisible revolution connect to the real world? Let's just ask that question directly. With all the old limits completely shattered, what new frontiers are finally unlocked? What does this actually make possible for us? Well, it enables the very future we are all talking about right now. The massive, insatiable appetite of generative AI for data, the split-second decision-making needed for self-driving cars, the sheer scale of the next generation of supercomputers. None of it, and I mean none of it, is possible without this new 3D foundation. It's the engine for the whole shebang. And I want to leave you with this final thought from the source material. As we stand here on the cusp of this new era, just remember, it's all being built on these invisible, microscopic skyscrapers of silicon. The part of chip making that nobody ever used to talk about has now become the absolute foundation for all the digital progress that's yet to come.